I guess. Oh, okay. Hello, everyone. And finally, I managed to find some time to do this online streaming of the topics related to my course in chemistry 320 on physical chemistry, specifically on quantum mechanics. We are studying right now, and today I will go through differentiation, integration, and also linear algebra, or whatever we have or we had actually in the homework number one. So I also have managed to learn how to use this cyber pad. So then I will be able to draw something on the screen and basically do all these derivations as on the blackboard or whiteboard. But of course, my drawing or um, writing skills are not so great. So, but that's not important. I hope it will still be useful for you if you haven't got the idea how to solve these problems. Okay, so let's just go through several of the topics we had in the homework number one. Number one is derivatives, and as an example, we had this Lennard-Jones potential, and we wanted to compute the forces which are negative derivatives of that potential with respect to the coordinate. So here is the paint file, and I'll start my drawing here. Okay, the potential U is like 4 epsilon, then big parenthesis open, then here have R over R sub-0 divided by R to the power of 12, and then minus the same stuff, same fraction to the power of 6. And now we want to compute the derivative of u, so the force is minus du over dr. So what we are doing is basically we first take, so think about this, you have a function of a function, and well, basically we have something like x to 12, where x is, r, the node over r. So then we basically have a function of that argument, which is also a function of another argument. So that's basically you're applying the so-called chain rule. Okay, so what that means is that maybe we can rewrite it this way: the u over the x, and then times dx over dr. That's still one-dimensional potential. By the way, this thing will be 4 epsilon, and then here have x to the 12 minus x to the 6. Well, actually, so let me see what we have in the homework. We have 2, but let's do just a general one, of course, not for 2. That's important. So I always want to deviate sometimes. And okay, so that's what happens, and you know how to take the derivative of that function is the simplest of the derivatives possible. So first the constant, this part, just stays unchanged, and then we differentiate x to the 12. That gives you 12 x to the 11 minus 6 x to the what, to the fifth. And we also want to multiply that stuff by dx over dr. Now, when we want to compute the derivatives of this sort of derivative, we will have r sub 0, which is just a number or constant, which basically goes away and goes in front. So you basically differentiate with respect to r a function which is 1 over r. and this result is 1 minus 1 over r squared. So you have minus here together uh, gives plus 4 epsilon r naught, and then you also have r squared, and then here we can recall that this what the definition of x was. So we now have 12 r dot r, and then here you have 12 minus 6 r to the fifth, and that's closed. Okay, so that's one of the examples. Now, what I'm doing, I'm closing here, will be a little bit more elaborate example. So we take a derivative of that function with respect to each of the components. So now this each vector will be, well, I mean, so you have a vector, right? So f is f1, for instance, is actually is a vector of three components minus du over dx1, and here is minus du over dy1. Oops, then I have to do 1 minus d over du over d1, and that all makes up a vector with three components. So then we basically want to compute each of these directions. So let me just start another one. So what we are doing is our function is 1 over r12, where r12 is the square root of x1 minus x2 squared plus blah blah blah, some constant. I mean, basically right now I'm going to differentiate with respect to x1, and from the point of view of x, all the variables here are constants y and z. So then, and then I can also do it in a more simple, so in a simplified way. Okay, so that r12 is basically an absolute value of r or r1 minus r2 vectors. And if you remember, well, I hope you do, or if you know that, so what is the absolute value of x, or of vector x? That is defined as a square root of a scalar product of the vector with itself. So that's like that. Now, if x itself is a multidimensional, so then it may have components. Let's say you have x as something like x1 component 1, x2 component 2, x3 component p, and so on. That means this thing will be square root of what? Of x1 squared plus x2 squared plus x3 squared plus and so on. All those things. Now also, but in our case, this vector is a difference. So I mean, in our case, x is a difference between of two vectors r1 and r2. So instead of these components, we'll actually have corresponding components of the differences. So, and with that, let me maybe, oops, I'll do this selection. Let's see how that works. Okay, that's not that bad. Alright, okay, so we are taking the derivative of that function with respect to x again. Now maybe let's call it this way, so that will be something like maybe a squared plus all that stuff, where a is the difference. So now du over the x1 will be du over the r12. Well, r12 is a number, is a scalar, so that's just normal derivative, then we do dr12 over what? Well, maybe we can also introduce this another function which is under the square root. Let's call it maybe z. So then we do dr12 z over dz, and then dz with respect to a squared. Oops, not squared, just a, and then dA with respect to x1. Now, what we can do? U in terms of 1 R2, that's that's R12 to the minus 1, so that gives, this part gives you minus 1 over R2 squared times. Now R2 R12 in terms of z is z to the 1/2, so that gives you 1/2, and then z to the minus 1/2. Now z in terms of a is a squared plus constant, so this derivative will be 2a. And then a in terms of x1 is x1 minus x2 squared. So actually here we can do this a little bit more elaborate again. So we can okay, so a is basically b squared, where b is x1 minus x2. So you can replace this thing as dA over dB, and then dB over dx1. So that will give you, so dA over dB is 2b times dB over dx1 is 1. Okay, now just collect everything and we'll get a result. Um, so maybe I will just erase something from here, from the top. Don't need this part anymore. So the result goes to be 1 over R2 1 squared, and then this 2 and this 2 cancel out. Now 1 over z, so this part is basically 1 over R12. Now a is to a is x so I guess I lost a little bit, but a in terms of, so z is okay. So yeah, the thing is I got it twice, so I get 2a, and then here I actually don't need 2b. Here I actually just have 1, because that part is so this is dA over dB, that actually goes to be 2b, and then times 1, so that is just x, I mean 2 and 1/2 cancel out, x1 minus x2, so eventually get minus x1 minus x2 divided by R12 cubed. And of course, because when you compute the force, you take negative of that, so minus sign will also cancel out. And so now, if you do this for all components, you will basically get something like oops, something like that. So f will be, so here have x1 minus x2 over r1 2 cubed, and next one will be y1 minus y2 r12 cubed. And the same thing for z. Let me just show on this example. Now, what you can see is this part is the same for everywhere, and you can basically put it in front as a constant. So that's this. In a vector, you will have just these components. This is y1 minus y2, and then also z1 minus z 2, which you can, I mean, this whole thing is, you can identify with just a, vector r12 as a vector. So eventually you get r12 vector divided by r12, 2 cubed. Here you don't have vector because that means that it is a scalar and it is an absolute value, the magnitude of that vector. Okay, so that was problem number 1. Differentiation. Now let's go a bit to these integrals and see how to compute them. Okay, whether I will be able to write them. Okay, that's a little of challenge. Okay. So first one we get something like cosine of x times, oops, let me actually check that. Yeah, square root of cosine, square root of cosine x times sine of x dx, and we want to compute an integral of that. So the key here is to be able to find the kind of so-called full differential, which are basically the inverted formula for the integration or for the differentiation. If you remember, d cosine x over with respect to x is minus sine x times dx. So that means, whoops, that's just sine. Okay, forget about it. And then from here you have d of cosine of x. And right now I'm being a little bit more rigorous in my notation. So that's full differential of the cosine function, which is a function of argument x, and that happens to be sine of x times another differential of x. So as you can see, here you actually do have this minus, which we can put here, minus differential of cosine. And here in the front, I'm rewriting it in this way. So that's what we get. Now that another way for the method is another name for the method is change of variable. So basically looking for the suitable change of variable. So let's call it y, will be cosine of x. So then you have minus y to the 1/2 times dy, right? And that integral you can of course compute, which is y 3 second, and then we have 2 over 3 minus from the first from that integral, and also don't forget about c, integration constant. Now basically then you just replace this y with cosine of x, and here's your solution. So I will not be rewriting this in the full form. Instead, we'll just go to the next one. Next integral is what? Yes, this one. So what we have is integral of x to the fifth dx 3 plus plus x to the 6. So again, now we can do this the other way. Let's guess that our variable y is 3 plus x cubed to the 6. Then let's compute differential of y. So what is differential of y? dy is basically the derivative of y with respect to x times dx, which is equal to the derivative of p is 0 and the derivative of that thing is 6 x to the fifth, and we don't forget about the x, right? So that's our change of variables, and that's how our differential changes. So then we basically want to reformulate this integral in terms of y, our new variable. So that then we have integral. This part becomes 1/6 over of the 1/6 of dy, and here have y, right? So and then again you can recall that the derivative of logarithm of x, whatever it is, with respect to something else, let's call it, I don't know, but let's make it the derivative of logarithm y with respect to x is 1 over, oops, no, with respect to y is 1 over y. So that means the full differential of logarithm of y is dy, we put it here, divided by y. So that thing, we continue it here, is the 1/6. We'll put the constant in front of the integral of the full differential of logarithm y. Now that of course gives you the integral of the full differential always gives you this function. So then you get 1/6 logarithm of y, or its absolute value of y, but in this case, of course, will always be positive as long as y x is a real number. So, but let's just do it in a formal way, and plus c. So that's the solution. Now let's do another example. So this example is solved similarly to these other cases. Now let's go to the case D. That's where we will need to use so-called integration by part. So we are doing this x times sine x dx. Right, again, that's why it's important to remember all this, to memorize all this differentiation formula, is that because that lets you see these full differentials in integrals. So that will be minus the cosine of x, and well, that's equation. So that then you basically have x d cosine x minus, and if you remember, it's du over dv is equal u times v minus, you flip u and v with respect to d, sine that's v du. Okay. Now what that means is that here's your u, here's your v, so then you basically have u times v is x times cosine x minus, and then you do flip thing, so v, which is cosine x, so you put cosine x, d, oops, du, and u is x, so it's that thing. Okay, now the cosine of And dx, that integral is of course as sine of x plus a constant. So eventually we get minus x cosine x plus sine x plus c. Okay, that's the thing. Now, what else? What else? What else? Okay, differential equations. I think that's important topic, especially because we'll meet it several other times during the course, and also it's common for other places. So let me just basically basically solving the differential equation is essentially where you need the integration, right? So the first one is first of is essentially the first of the chemical kinetics model. We get rate is proportional to the concentration of some substance, and this is also the uh, something that you will have in quantum dynamics as well, because that's essentially time-dependent Schrödinger equation in a given basis. So it has the same form. So now what you do with this equation, you want to bring all variables of the same type to one side of the equation. So C is the C of t. So C is a function, t is the argument, and that means you want to kind of separate them. So you basically dividing everything by C, and multiplying everything left and right hand side of this equation by dt to get minus k dt. Now, the next thing is you just put this integral sign here and here, and you want to compute the integral. Right, this one we just had in the previous example, that's your logarithm of c. Well, in principle, absolute value of c, but we'll assume it's always non-negative. And that's also a simple integral that gives you minus k times t, and what each of these integrals will come with an integration constant, but you can always bring one of these constants to another side. So you may actually have only one. You may need only one integration constant, it's called a tilde, and then your solution will be c of t is exponent of a tilde minus kt, right? So, and then if you define a to be e to the a tilde, then you can define it times e to the minus kt. That's the kinetics. So that is the general solution, but in this problem we are asked to find a specific one such that c C of 0 is 1, and that's actually the condition that allows you to find this integration constant a. So if you plug 0 as a argument, you basically get C of 0 is a times e to the 0, which is 1, so that's a. Right, so and you know that this one is 1, so that's what you get. And eventually your solution will be C of t 1 times e to the minus kt. That is the solution. Okay, that was the first order differential equation. We want to look at the second order differential equation. And of course we're dealing with the homogeneous ones. Let's look at this one, for instance. Okay, so oops, go here, y double prime. Okay, I already forgot the equation. What plus? Okay, and then 6. Okay, so then it's plus y prime minus 6y is equal to 0. Now, so the idea is that you first want to solve the construct and solve the so-called characteristic equation. Basically, each prime is nothing but the differentiation of function y with respect to its argument, right? So if you have y is y over x, then y prime is dy over dx, and then y double prime is d2y over dx2. Now you can also think about function itself as being the zeroth order differential derivative of the function, right? So now each order is replaced, so each order gives you the corresponding order in some variable lambda. So that's right. So then you basically solve it. 1, 2 will be minus this is minus 1 plus minus square root over 1 squared minus 4 times 1 times minus 6. That gives you plus 24, and together that's square root of 25 divided by 2, so you have minus 1 plus or minus 5 divided by 2. If you choose both minuses, that gives you minus 6 divided by 2 minus 3, or if you choose this plus, that's 4 divided by 2 is 2. So the general solution will be, okay, actually let me do this. I will erase it, oops, no, I will erase it here. So I found this solution, I will erase it here. And here I'll just continue with the general solution, which will be y over f of x is c1, first integration constant, minus 3x plus c2 e to the 2x, right? So the second integration constant. Now let me clean this part of the document. Go back here. So that's our general solution, and what we want to do now, we want to use our boundary conditions or initial conditions, whatever you think about it, and we have y at 0 is 1, y prime at 0 is 0. So we go here. Well, first of all, let's also compute y at 0. What will it be? If you put 0 here and here, it's 1 and 1 here, so you basically have c1 plus c2, and that is equal to 1, right? That is equal to 1. If you look at the y prime, which is derivative of y with respect to x, so that actually minus 3 c1 e to the 3x plus 2 c2 e to x, and then you have y prime at 0 will be minus 3 c1 and then plus 2 c2, that gives you 0. So that means you can express c1 as 2/3 of c2, and then together they give you 1. So that means 5/3 of c2 is 1. So c2 is 3/5. Now, and then c1 is of course will be then 2/5. So then your specific solution will be x, while x is, let's put one fifth in front here, and we get 2 e to the 3x plus 3 e to the 2x. Yes, that is the solution of the second order differential equation, homogeneous, of course. Now, so I guess this material is more or less simple. Let's go here to some other topics that sometimes cause a little bit of difficulties, and specifically operators. We talk about we want to compute an action, the action of these two operators in some arbitrary function f of x. Okay, so first, first operator is what is d over dx x that is squared, and it acts on the function f of x. So what the square of the operator means is it basically a sequential twice. It's a double application of the operator to the function. What that means is this. Okay, and again, so that's basically 4 sub-operations. So the operation here produces the result, which is basically a function f multiplied by x. So what happens is this: we have this. Okay, the x times f of x. Now here I didn't put this hat here to signify that this is the result of this first operation. Now we'll think about this operator. It acts on the result of the previous operation. That means this product x times f, not only f, not only x, but the product. So that can also be represented in this way: dx times x prime, and then times x times f prime, right? And this one is what if you remember the rule, uv prime is u prime v plus u v prime. You basically distribute this prime here and there, and here of course you have multiplications. Now what that gives you dx over d over dx, x as an operator, and here's f plus x f prime. Now we'll think about this operator. It acts on this whole function, the sum, to multiply the sum by x. So we get dx acting on what? On x times f plus x squared times f prime. And again, this thing is nothing but the prime over all this expression, which gives you this. So now again we have a sum of two products, and then we take the derivative of that sum. The derivative of the sum is the sum of derivatives, and then each derivative is a product. So then you basically have x times f prime plus f, and then here have 2x f prime, and then plus x squared f double prime. So now if you close it, that's your result essentially. What you can also do, of course, you can notice that this and this terms are similar, and then you can also represent these primes as operators, some operators acting on the function. Now, and of course, the order is important. So we could write it this way: x squared d over dx squared plus, because of these terms, I have 3x and then d over dx and then plus 1 acting on the function 1. And here you can basically put a hat to signify that these are now operators that act on the function. Okay, so that was this example. Now let's also talk about the second example here, because this may be a little bit also confusing. So what happens is you have d over dx plus 1 everything squared acting left, and you basically apply the same rule, dx plus 1. And here's the first application of this operator, 2f. Now, what happens here is d over dx acting on f makes a derivative of x of f, and this one acts on f makes just f, so it doesn't change it. So first I rewrite this part of the operator, and the second one, like I already explained, I will already write as a result. Now here we have this operator being applied to this new function, which is f prime plus f, and the algorithm is exactly the same. So first part of the operator acts on it to differentiate each component so that you basically get f, or maybe let me put it this way, f plus f, everything is prime, plus 1 doesn't change it, so you just have f plus f. And from here you have prime of prime is double prime, f double prime, plus f prime, and I can already combine it with this prime, so it's 2f prime and plus f. So that's basically it, right? Now, so for these operators, the commutators, that's exactly the same idea as applying operators of this sort. And by the way, let me see if there is anyone looking this session. I don't know if there is any way to check it. Somewhere I used to have it, but okay, doesn't matter. Let me just go ahead and do this little exercise. Well, two more little exercises. One is for matrices and another for just vectors. Okay, so we have this matrix like Hamiltonian, and here is some transformation matrix. We want to compute this C plus and C. Okay, what happens is so oops. So you have C matrix is C so S minus S. So where I just denoted the C is a cosine of P and S is a sine of P. Now what the C plus means, or C dagger, is a transpose and complex conjugation of this original matrix, because all the components here in the original matrix are real numbers, so the complex conjugate of it is basically the same. What the complex conjugation means is that you take any function of like a plus I b and convert it to, I mean, the functional form stays the same, but everywhere where you see I, you just change the sign to the opposite. Oops. No, like not like that. But then after this communication, you need to transpose. So that transpose means everything on diagonal stays on the diagonal. So C is C. Everything from and basically just kind of reflecting elements, across this diagonal. So this S will go here, and this minus S will go here. So you will have minus S and then S here. And then if you, okay, that's basically the exercise on matrix multiplication. C S minus S C, and then this is just what? So this element, what you do, you multiply this C times this C squared plus this S and this S squared. So for this element, what you go this row and this column, C times minus S, C times minus S plus S times C. S times C, which actually gives you 0. Now, what happens here is you multiply this row and this column minus S times C plus this C and this S plus C times S. Again, that whole thing gives you 0. And this one is the first one, as you can notice. Final element here is minus S, that is S squared, and then C and C squared. That's 1. So the result is the identity matrix 1, 1, 0, 0 here. Now let me just explain this idea. I found that once convenient way to explain. So let's say you have 2 and then that's actually 3. Okay, that's 4 plus we'll just have it 4 minus 3 and 0. So these are rows 0 and 1. These are columns 0 and 1. If you want to compute let's call it A. If you want to compute a transpose matrix or matrix elements of the transposed operator, uh, so or not operator of the matrix, you basically go by that. So this is A transpose 0, 0, A transpose 0, 1, A transpose 1, 0, and then A transpose 1, 1. That's how you basically define this matrix. Now, the definition of the transposition in terms of elements is indices is this: is you change the indices j here. So that's what that becomes A 0, 0, because so here's your I is 0, j is 0. You change them in the order, you get 0, 0. Here you get I is 0, j is 1, so that becomes A1, 0. So that's A1, 0. By the same technique, we have A0, 1, and here's AA1. So then let's take a look on it. So A 0, 0, this is diagonal element of the original matrix. That will be 3. Then A1, 0, this is actually this element minus 3. So it goes here minus 3. This one is A01, so that's 8, 0, and 1. So that's 4, and this one is 0. Okay, so that's how you transpose matrix. Let's say we have another type of matrix, 2, 1, 0, and then minus 2, 0, 3. Okay, what do we do? How do we transpose that matrix? Well, let's look at this. So we want um, you can think about this again. I goes in this direction. That's I in 0 and then 1. And here is your J going 0, 1, and 2. So then you have element A, that is our A matrix. Forget about transpose for now. A 0, 1 is 2. Then will go, if you flip it, it will go to 1, 0. So let's think about it. So that's second, or the, well, basically the row 1 and column 0. So if you have some sort of matrix, then you should have it here. So that 2 goes here. Now then a 0, well, that was actually 0, 0, and goes to, no, that goes to 0, 0, so that's actually here. Now a 0, 1 is 1, that goes to a 1, 0, 1 is here, 0 is here, so that becomes 1 here. The next one is a 0, 2, which is 0, this number here, and that will go to a 2, 0. So 2, that means you have a row 2 and a column 0, so it will go here. This 0 will go here. Now let's just do the same transformation with this matrix elements. You get a what 1, 0, which is minus 2, will go to a 0, 1. So it's a zeros column, but a zeros row, but the first column or column with index 1 actually. So it's minus 2, and then a what a 1, 1, which is 0, will go to A11, nothing changes, but it becomes here. And then finally A12, which is 3, will go to A21. So 21 is here and here. That's 3. So that means that this will be the structure of our matrix. Now it's 3 by 2. But we started with the matrix 2 by 3. So that's the idea. When you transpose matrix, you also kind of flip it or rotate 90 degrees in this plane. So that's what happens. Kind of structure. It's important to remember. Okay, and then I guess the final exercise for the day will go through this example for state vector and vector multiplications. So first we want to compute the normalized vector, and our vector is what is C, which is okay. I forget it. 1 and 1 plus I. So this is 1 and 1 plus I. Now here we have complex valued components of the vector, and we want to compute the norm of the vector. If you remember, we already actually talked about today, the norm of the vector is the scalar product, the square root of the scalar product. Now, the scalar product in case um, of the complex valued vectors, you can think in terms of C plus and C, where C plus is the transposed and complex conjugated vector. You basically need to transpose and complex conjugate this vector. By the example we just discussed, when you transpose a matrix or vector 2 by 1, you will get something 1 by 2. 1 by 2 is this. So you have something here and something here. Vector C is 2 by 1, so it has this structure. Now the numbers, C is just original numbers, 1 and 1 plus I. Here, we need also to complex conjugate. 1 is real numbers, nothing changes, but here have 1 and I, and we need to change plus sign to minus sign here. And then we basically do the matrix multiplication. 1 times 1, that's 1, and then plus 1 minus I times 1 plus I, so that gives you 1 and 1, 1. This and this gives you 1, and cross product cancel, that's 1 plus 2, together is 3. So, and that means this thing will be square root of 3. Now, if you want to compute a density matrix, so-called, as it's described here, so you do the opposite multiplication of the different structures. So you get 1 and 1 plus I, you can multiply it by this row 1 and 1 minus I. Now, when you use this sort of multiplication, you get a matrix which is composed of these elements. So this element will be here 1 times 1, which is 1. Next one is 1 times 1 minus I. That's 1 minus I. Here's 1 plus I times 1, 1 plus I. And this will be 1 plus I times 1 minus I will be 2. So that's the result. And answering the last question of that homework here, you basically, when you compute trace of a matrix is just a sum of the diagonal elements. So you basically add up 1 and 2. 1 and 2 gives you 3. So in this case, trace of the density matrix composed, constructed from this sort of state vector is the same as the norm of that state vector. Okay, so I hope this little tutorial or video was useful or will be useful to some of you. And I thank you for your attention, and have a good day or whatever time it is now. No, ничего такого. Что надо искать? Save. Okay. And, mentioned.